All right, the final rating will be taken as 4. So the idea is very simple. Predict the target variable using any machine learning techniques. The main causes of differences in actual and predicted values are noise, variance, and biases. Ensemble helps to reduce these factors. So why we are using ensemble methods? To improve the performance. And what are the issues in predicting something? We have those issues: noise, variance, and bias. Or more simplicity, I will say that noise, overfitting, and underfitting. So these are the new names for underfitting and overfitting. Variances and bias we will discuss later in the lecture. To address those three issues, we use Ensemble to reduce these factors. Okay. Okay, so max voting is a simple technique for ensembling. There is another one. All right. So ensembling. Ensembles are two types. One is bagging and another is boosting. In bagging, we have like random forest, which handles overfitting, reduce variances, independence classifier, and boosting. Uh, the boosting types of classifier are gradient boosting. And what is the difference between these two? Independent classifier means every classifier, every classifier is independent to the others. While in sequential, in ensembling we use more than one classifier, as I told you. Yeah. You have model 1, model 2, and model 3. So you send an input, and the model will predict something, and same is here and same is here. So they are not independent to each other. You just count them. That what is the prediction of the first one? Let's suppose it says 1, and what is the prediction of the third one? It says 1, and what is the prediction of the middle one? It says 2. So max voting says that we will take the majority as a decision, as a final decision, and these are called independent classifier. While in the sequential that we can see in boosting, every model's output is actually an input of the other models. So here we have model 1, 2, and 3. I already have discussed in gradient boosting that I'm not going to repeat here the whole idea. The classifier 1 will predict some will predict the values, and among them some of them will be correct one, right one, and some would be the wrong one, and the wrong one will be assigned some weight, and this model will apply on the wrong one, and that model will predict, and obviously some of them would be the right prediction, some would be the wrong prediction, and the wrong prediction will give a higher weight, and then the model 3 will apply on that set, and the same fashion will goes on and on. So this is a we can say sequential classifier. So the bagging, this is a classifier, and this is another one, this is another one. So this is a parallel, you can say parallel pattern, and this is a sequential one in the boosting. First this is the data set. We gave it to a model. The model predicts something, and we will get some wrong predictions, and you can see some points are are very bold. These means we have given them a higher weights. And another model is applied, will be applied on the data, and this will go same way. Uh, I have a slide and I have a lecture on gradient boosting on this. All right, so here we have an example of our max voting. You have a classifier, this tree classifier, decision tree, model 1, and the model 2 is actually k neighbor classifier, and model 3 is a logistic regression. So you have three models. So as usual, you just give the trained data to model 1 and the same data you gave it to model 2 and model 3, and these model will predict something, prediction 1, 2 and 3, and then you can find out that what are their predictions. You just get the you just count them and make a final decision. This is the same one. We are using voting classifier, a built-in function that sklearn has. So you have model 1, model 2 and you have two models here. So this is the built-in method, voting classifier. This is the model 1 and model 2, and we are going to do hard voting, train the model. So this is the model, and this model has two models inside, 1 and 2. You just give them train data and the train label, and once you fit it or trained it on this, we just give them the test data and will give you a score. Any question? It's pretty simple. The only new thing here is this one, voting classifier. What it does, I told you, it does like this one. It does this. This is the model 1, model 2, model 3, model 4, model 5. Each model give you a prediction on the same data set, and then at the end you can count them. Now just count them, which one is in the majority. Obviously 4 is in the majority, 1, 2, 3. So final decision is 4. Okay, averaging. The idea is same, nothing is changed. The only change is here. We are going to make an average. So add them 5 plus 4 plus 5 plus 4 plus 4, and you will get something, and then divide them with 5 and you will get an average. In this case, we have an average 4.4. So the final decision is 4. So this is the decision tree classifier. We have a k-neighbor classifier. We have logistic regression classifier. We are using 3 classifier. You would have data. Let's suppose this is the data. And the data, you just divide it into train and test. So you have train part and the test part. So trained the model 1 and train on the same data set the model 2 and similarly the model 3, and then provide the test data to these models and find out what are the prediction, and then find the average, and the average will be the final decision. So is it any question? Is there any question? Speak up, boys. Any question? Hello? आवाज आ रही है आपको? Oh, okay. No question. All right. Hmm. Good. Sorry, where was weighted average. So you guys know that in real scenario, not everyone has the same experience. Okay, in real world, like in our class, no one is expert on everything. Some have expertise in some field, and some have some other. For example, in our friend circle, some guys are good in watching movies, and he or she has more experience. And if we ask them how that film is, how do you rate that film, so the expert will rate, we will give them a weight, the one who has more experience. So here the same idea we are applying in our model. So for example, this guy has weight 23, this guy has weight 0.18, and this guy has 0.23. So whatever this guy predict, we will multiply with the weight. And if this guy predict anything, we will multiply with this weight, and at the end we will add them. So the same idea, these are three models, and we fit them, and uh, then we apply the test set. We got a prediction 1, 2, and 3. Prediction 1, the model 1, we gave 0.3 weight to model 1, 0.3 weight. And to prediction to model 3, we gave this model a bit higher weight, 0.4. So the weight will be multiplied by the prediction, and at the end you will get some result. Okay, sorry. Okay, we have advanced ensemble techniques. And in advance, we have stacking. So you stack model one after the others, one above the others, and at the end you build a model that is a combination of different models. So how it works? Stack is an ensemble learning technique that use the prediction from multiple models. This model is used for making prediction on the test set. Okay, so how it works? For example, you have a training set. This is the training set, and this is the test set. As a whole, this is your data. So you separate your test set as usual, and you make subset of your training. Here I have subset. I have 10 subsets of my training set. Train your model on these 9 and validate it with this one. And the next time then you train with you trained with these from 10 to 2 and validate it on set 1. Okay. Split into 10 as a base model. For example, we are taking decision tree as our base model. The base model is trained on the 9 subsets, 9 parts. You trained your decision tree on the 9 parts. 9 parts are these. These are your 9 parts. And this is done for each part of the train sets. Okay. So at the end, you will have this. You will get a decision tree subsets. For example, on this training data, on this validation, you will get some output from decision tree. And if you, for example, give a data that is the decision tree will predict something, and these prediction we will keep it here. And same we will hold on. I need to let somebody in the online class. Okay, so once you have a decision tree, then you will take another classifier, repeat the same steps. What are the same steps? These are the steps you have to do. Divide your test into 2, train and test, and then make subsets. Like here I have 10 subsets. So out of 10, train your model on 9 and validate it on the 10th part, and do the same. Do the same for each part of the training set for the specific classifier. Now take another classifier KNN, and you will have these sets. At the end, you will have decision tree predictions for the for a set, and the KNN prediction for a set. So take those predictions as the features and apply the test data. Okay, so this is an example. You have a method. Start from here. You have a decision tree classifier. You can see this is a decision tree classifier, model 1. So this is our function. We are sending we are calling function stacking. What we are going to send, model 1, this is our model 1. Unfold means how many subsets are you making of your training set. So 10-fold. This is our training data. This is our test data. And this is your y_train is the labels for the train data set. You call them, you just call this function, and it will predict and return those test prediction and train prediction. So these are the prediction on the training data, and these are the prediction on the test data. Just put it into Panda data frames. So train_prediction 1, and and save test underscore prediction. So you are going to save those test prediction and train prediction in a data frame. Now, take another classifier, KNN. This is the KNN classifier model 2. So same, you are calling stack function. You are passing this function model 2 as a model, and the number of subsets of the trains are 10. Your train data set, this is the test data set, and this is the labels for trained, and you will get back these two things. These are all predictions based on training data, and these are all predictions that are based on that is based on test data set, on the test data set. This. So you just save those two into data frame. So in the data frame you have stored train prediction, test prediction, and same here you have stored train prediction 1 and test prediction 1 for decision tree. Now you just concatenate those two results. You have here concatenated the test results and train results. Apply logistic regression. Make a model. First make a model logistic regression and apply the logistic regressions on DF. And what is the DF? DF is this. And Y train is the label. So this will then give you some prediction score. So basically what you have done, you have taken DT, decision tree, you have taken K neighbor, KNN, and combine the results of DNN and KNN. What are the results? Train prediction and test prediction. Train prediction and test prediction. Combine them into one. These become the features. And then give those features to logistic regression. And logistic regression will then, you just give them give logistic regression a test data, and it will predict it for you. Blending. After stacking, we have another complicated classifier for ensembling is known as blending. So it's just same as the previous one, except that it holds a part of the training data. For example, this is your train set, this is your data set. You just divide into two, one for test set and other for training set. This is for training. In the training, spare some of the part and call it validation. Okay, validation. Train your model on this and test on this. Validation plus test. So this is the difference between blending and stack algorithm. Let me remove it. All right. So you have train set. In the train set, you have two parts: training set and validation set. And this is the test set, as usual. So you have decision tree classifier, train on this part, train on this part, train on this part, and validate on this. Validate means when you trained it, just give the value from the validation and find out what are its predictions. For this validation, you will get some output, and for another point you will get some output, and for another point you will get some output. So you will have these things. Same for DT and Canon. Once you have this, you just use test set for evaluating it. So here you can see the example. Model 1 is the decision tree. Okay, so there is nothing new. You have decision tree. The students are keep coming, so let him in. Sajid Iqbal. Okay, look. This is the model 1, a decision tree. You have a data set, X train and Y train. So you have data set. This is the train and this is the test. And this is X value and these are the Y value. Y are normally are labels and X are the points. So these are X points and these are the labels. Okay, so you create a model 1. Then these are validation subset. So in the train, you just reserve a part, a subset, and call it a validation part. So you just use those validation part for the prediction. You will have validation prediction 1 and test prediction. And for the test prediction, you use test data. So now find out, okay, so put those results into a data frame, okay? So data frame means just put it into a table like this one. There is input, you get a prediction, there is a value, there is a prediction, there is a test, there is a, for example, in this case, value will come here and the validation prediction, sorry, here. The X test value will come here and the prediction will come here. So to making into a table, to save into a table, we use data frame. All right, so data frame is nothing so horrible thing or some alien. Okay, so take another classifier, K-neighbor. Model 2 is a K-neighbor classifier. So same here, like we take a train data and the label, and you have a you train your model 2 on the training set, and then they take validation values, those validation values, and find out some prediction, and then take test data and find out the prediction, and take these two values into data frame. So here we are going to do. Okay, let me remove those ugly drawings. Okay. So you have those values and those values. Put them together here. Make a concatenation for validation values and test values. So again, you have data frame You have validation values and test values. Then now make create a logistic regression model and fit the model with DF values, validation values and the labels, and find out once you have trained your model with on this, then use those values for the test, and it will give a score. It will give you some accuracy. So here you combine two models, and then uh, you have used third model to predict, to get our output. Sorry, you combine two models and they did some predictions. So those predictions serve as an input for the third model, and the third model is giving you, the final model is giving you the prediction on the test values. So we are investigating ensemble techniques where more than one models we can apply, and those more than one models can be applied in different ways. There are two major types, simple and complex. So the simple one was max voting, averaging, and weighted voting. And in the complex algorithm, we have gone through stack and blending, and next is the bagging. So the idea behind bagging is combining the results of multiple models. So you have a data set and you apply it to multiple models. All right, so if you give it to a model 1, for example, to model 1, M1, and then M1, and the same data set to same model, will that make some improvement? Hmm. No, it will not make any improvement if you have same data set and same model, M1, same model, M1, same model, M1. That will not improve. If you want to make the same model, but if you make a subset of your data and give it the first subset to model M1 and the second to model M1 and the third give it to model 1, then you might have some different results. So this is the basic idea behind bagging. Bags, subset means bags. So we are going to look into it. One of the technique is bootstrapping. That is a sampling technique in which we just take samples. We create subsets of observations. Means from your data set, you get subsets from the original data set with replacement. With the replacement means if you, for example, you have that much big data set, okay, and you get this subset. This subset is not of the same size as the whole data set. So you just make copies of it and it will make you the same size. So keeping the same size, replace the other ones with those subsets. This will done by the algorithm by itself for you. Okay, the size of the subset is the same size as the original set. Bagging techniques uses three subsets. It uses these subsets to get a fair idea of the distribution. The size of subsets created for bagging may be less than the original sets. So here you can see original data, you made subset D1, D2, D3, D4, and D5. So this is the idea how you can make subsets. And multiple subsets are created from the original dataset, selecting observation with replacement. A base model means weak model is created on each of these subsets. These models run in parallel and are independent of each other. The final predictions are determined by combining the prediction from all the models. So you got subset 1, subset 2, subset 3, subset 4, and subset 5, and give the data to model 1, model 2, model 3, model 4, and then combine the predictions. Okay, so okay, feature selections. Can you guys tell me why features are important? Any idea? Just for the sake of discussion. Bushra, why feature selection is important? Is Bushra here in class? Okay, Shahzad Hussain, can you tell me why feature selections are important? Feature selection means you have a lot of features and now you want to find out, you want to select those features which are very important, which plays a vital role to classify things. Feature selection is one of the core concepts in machine learning which hugely impacts the performance of your model. If features are not, if features are poor, the performance would be good or bad of the machine learning, of the classifier. Shahzad Hussain, what is your views on it? Anyone? Fahim Mushtaq? Too bad.
Yes, sir.
If our features are poor in performance, what would be our model performance? Would it be good or bad?
So bad ही होगी सर ये हमारी अगर फीचर अच्छी नहीं होंगे फीचर सिलेक्शन अच्छी नहीं होगी तो
If our features are poor in performance, our model would be bad. So here comes feature selection idea. We have to select those features that are playing important role in discriminating or in classification to discriminate two classes. All right, so the data features used to train your machine learning models have a huge influence on the performance. Feature selection and data cleaning should be the first and most important step of our model designing. First, you have to select the features, and then you have to do data cleaning. Feature selection is the process where you automatically or manually select those features which contribute most to your predictions variables output in which you are interested in. So you might have lot of features, for example 50 features. You have a data set and you have 50 features. Normally if your data set is, let me uh, let me ask something from you. If our data set in a table format, if our data set is in a table format, in table you can see there are rows and columns. Okay. Normally our data set comes like this, rows and columns. So normally the columns names are our features and the rows are instances, are data points, data point 1, data point 2, data point 3, data point 4, and the columns are features. So for example, you have 50 features. So it is not a good idea to use all 50 features for the classification purpose. So you need to find subset of those features. Select features that are more important to classify any data. Okay, having irrelevant features in the data. So if you have irrelevant features in the data, that will increase noise and that will reduce your model performance. Okay, class, uh, is Bushra here? Bushra, what is the question? Can you read this for me? Is she not in? Okay, Bilal Faiz, can you read this? Can you read this? What is the question?
Yes, sir. Sir, it says how to select features and what are benefits of performing feature selection before modeling the data.
Okay, this is very important question, okay? So
Yeah.
how to select features and what are the benefits of feature selection? If
Sir,
this if this question comes into some test, then you have to answer this.
sir,
What are the feature selections techniques and why these are beneficial? So feature selection techniques that are easy to use and also give good results. So these are the techniques: univariate selection, feature importance, correlation matrix with heap. You have to know the idea. Otherwise, Skylearn has all built-in methods for you. Look at the data set. This is a data set of a mobile shop, you can say, and it has the features of a mobile. Mobile has a battery power, whether it has Bluetooth or not, what is the clock speed, does the mobile has dual SIM, does it has frontal camera, what is the megapixels of the frontal camera, what is the internal memory, how many cores are there, and mobile depth in centimeter, mobile width, and has it 4G or not, primary camera pixels, what is the megapixels of the primary camera, pixel height, pixel width, RAM, how much RAM it has, does it has Wi-Fi or not, screen height, screen width, and the longest time that a single battery charge will last when you are Like if you are talking on the mobile whole night, how long it will take for a battery to discharge? Does it has 3G or not? Touchscreen, it has touchscreen or not? So this is the data set and these are the features. And we want to classify them. We have lot of data, we have lot of mobiles, and we want to classify based on these features, and we are going to find out that which features are not so much importance. So we will remove those features while doing classification. So let's move forward. So univariate selection. Statistical test can be used to select those features that have strongest relationship with the output variable. Okay, so we have output variable and input variable. So these are all input variables. We will take only those input variables that has strong relationship with the output. So the scikit library provides us a select k best class that can be used with a suitable of different statistical test. So select k best. For example, if you want to apply a built-in method, you would say that I want to see 5 best features from this data set or 10 best features from this data set. So the example below use the chi-square statistical test uh, for non-negative features to select 10 of the best features from the mobile price range prediction data set. So you can see we have imported some libraries, and this is the library that has k-best, select k-best features, built-in library. All right, and we have imported chi-square library as well. Here you get the train data set, read the data set, these are the CSV values. And what is this? This means, if you see this, so the from left to the column, this indicates rows. Means this part indicates rows, and this after column indicates columns. So you can see here before column there is nothing, no value is here. So this means all rows. And after column we have a comma, and here we have C 0 to 20. This means columns. Columns 0 to 20 columns. This means 0 to 20 columns. So this will give all the values, all the 20 columns values to this, independent of the rows. Let's suppose I have, for example, I have 3, and this is the column, and I would say 0, comma, 0 to 20. This will give me 3 rows of, of 20 features. If I use this 0, 3 and 0, this means it will give us 3 rows and 3 columns. 3, 0 to 3 means 3 columns, 3 rows and 3 columns. If you haven't anything here, this means all rows. So you will get all rows from 0 to 20 columns. Okay, let's move it. All right, so here you get the labels and you are applying select k best score functional. Which score function are you are going to use? There are many. We are using chi square. And how many features you want to know? 10 best features I want to know. So the best features will come here, and you can best feature dot fit, and you just put x values and y values, and at the end you just display them. You will get this. So these are 10 best features, and these are the score. So you can see RAM has highest score. So 931,267. And after this, the px height is the important feature. And battery power is the third one. Pixel width is the fourth one. And at the end, you can see screen height and frontal camera has least. So it gives you 10 best features that can classify mobiles based on the prices. Here you have, I don't know how many features are these, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 20. So out of 20, you got 10 best features. Okay, feature importance. Okay. In feature selection, you have three techniques. One was the univariate selection, other is feature importance. So now we are going to get feature importance. Feature importance of each feature for the dataset can be obtained by using feature importance property of the model. So every model has a property. Feature importance is a property, and every model has this. Feature importance gives you a score for each feature of your data. The higher the score, more important is the feature is. So here we are, we have an example of extra tree classifier. So look at this, the same data. We are taking trained data set, and from there we get all the data except the label, and the label is put into Y. And now this is extra tree classifier model, and we fit the model, means we trained the model on the data. And the model has a feature model dot feature underscore importance. We print them. Just print them, and you will then get it like this. So this is a plot, and you can see the RAM is the highest value. It is like 0.4, and after this is the battery power and the pixel weight, pixel height, mobile width, and mobile depth. So these are all. This shows the feature importance of each feature. So feature importance is a built-in method of each model. You can use them as well to just see which feature is important. Correlation matrix with heat map. Okay, heat map is a plot, Heat map is a plot. It is a two-dimensional plot, and in the two-dimensional plot you have different colors. Each color represents different values, and you will see in a moment. So the same data set, everything is same. We got columns X, all the features in X, and the label in Y. Data dot CORR correlation, and we got a matrix. Correlation mat dot index. These are the features, and we are making figure size 2020. So we are plotting it, and when you plot this, these are the plot features. When you plot it, you will get it like this. Let me take magnifier for this. Here you can see these are the columns, feature names, and here these are the same feature name here as well. So you just look at RAM. Where is RAM? Where can I find RAM? RAM. Yeah, this. Look at this. RAM has a relation with this is RAM. RAM is a feature. RAM has a relation with price range, and you can see very strong relation is 0.92, and the RAM has a relation with this feature is 0.023. So from here you can see that which feature has correlate with other features and how strong is it. Oh, sorry. For example, this feature, for example, this feature has strong relation with this feature, and the value gives you an idea that how important is that feature. And this is the bar, and if you go into the bar upside upwards, you will have higher, you will get a higher values. Okay, so why is it beneficial? Because it will reduce overfitting. The feature selection, why feature selection is important, and why, how is it beneficial? It reduces overfitting, it improves accuracy, and reduce training time. So if you select, like in previous example, if you select 20 features, it will take more time in training. But if you select 10 features out of 20, probably you will have half of the training time of the 21. Methodologies and techniques to subset feature space. So what are the methods to subset the feature space? There are different methods. Filter methods are generally used as a pre-processing step. The selection of feature is independent of any machine learning algorithm. Okay, when you going to select some features, it doesn't have to do anything with the machine learning. So it is independent of the machine learning. Features are selected on the basis of their scores, not on the basis of the model or classifier. Like I'm not going to select my features to consider SVM or any other model. I will select features based on its score. Very statistical test we can use to find the best features. So set of all features, we have set of all feature, we select subset, learning algorithm, and then performance will be increased. So the correlation of is a subjective terms. For basic guidance, you can refer to this table. If your feature are continuous and the response is continuous, you can use correlation, Pearson correlation. If your features are continuous while response is categorical, means prediction is categorical. Categorical means discrete. If then you can use LDA for correlation. If your features are categorical, like dog, birds, and some other categorical classes, and your output response is continuous, then you can use Anova. If your feature is categorical and the output is categorical, then use chi-square. All right, so let me in some students. So Pearson correlation It's a measure of quantifying linear dependence between two continuous variables x and y. Linear dependency. Its value varies from -1 to +1. Pearson correlation is given as by this formula. Xy is the correlation and divided by the mean of x and y. Linear discriminant analysis is used to find a linear combination of features that characterize or separates two or more classes of a categorical variables, as can be seen on the table. Anova analysis of variances is similar of LDA except for the fact that it is operated using one or more categorical independent feature and one continuous dependent. So one categorical and one independent of categorical. Chi-square is a statistical test applied to a group of categorical features. So categorical features to evaluate the likelihood of correlation or association between them using their frequency distribution. Wrapping method. Wrapper method, a subset of features used and train a model using, for example, you have features and you just apply subset of the features and then find out what is the performance. If performance is bad, then add more features in the model and then find out the performance, and you just keep on adding subsets or removing the subsets and then adjust the performance. So this is called wrapper method. For example, in the previous case, we have 20 features. So you just try with 10 features and find out the performance. For example, you got performance 70, then try with 15 and see is it going to increase from 70 or decrease. If it is increasing, then keep increasing, adding more features. So improving the performance that way is called wrapper method. And the wrapper method has three methods: forward feature selection, backward feature selection, and recursive feature elimination. Forward feature selection means, for example, you have 10 features total. You just try with the minimum first. Just train your model with 2 features and find out the performance. And then add 2 more features, make it 4, and then find out what happened with the performance. Is it going to increase? If it is going to increase, it just keep adding features and end where your performance starts degrading from some higher points. This is called forward feature selection. And backward feature selection, like in our previous example, just take 20 features and train your model with the entire data set with all features. You will get some performance. For example, your performance is 40%. Then start decreasing. After every removal of the feature, check the performance. With backward selection, you will observe that by removing features, your model performance will get better and better and better, and at some stage it will start decreasing. So these are methods you can use for improving the performance. Okay, so bias and variances trade-off. So whenever we discuss model applications, it's important to understand prediction errors. There is a trade-off between models' ability to minimize bias and variances. So bias and variances are 2 parameters, and we want to adjust them to improve our performance. Gaining a proper understanding of these errors would help us not only to build accurate models, but also to avoid the mistakes of overfitting and underfitting. So we need to get some understanding of bias and variances. What is bias? Bias is the difference between the average prediction of the model and the correct value. Means the model predicted something and then compare that prediction with the actual value. So the difference between these two is a bias. Model with high bias pays very little attention to the training data and oversimplifies the model. It always leads to high error on training and test data. And what is the variances? Variance is the variability of model prediction for a given data points or a value which tells the spread of your data. Like if you give your some data to your model and it predicts at one time good and another time it predicts wrong. So this is called variances. Model with high variances pays a lot of attention to training the data. Means it make lot of attention on training data. It is too much trained and doesn't generalize to the unseen data. And the result is overfitting, and the overfitting is actually a variance. Bias error from incorrect modeling assumptions and variances errors from the random noise. So mathematically, you have like y is the prediction and x is the covariances and e is the error. So the error is actually the sum of bias square, variances, and an irreducible error. Your error comes on these three factors: bias, variances, and an irreducible error. You can control these two to some extent, but the irreducible error you cannot reduce, you cannot remove this. This is all the data set has this irreducible error. Okay, this is called bull's eye diagram. Bull's eye diagram. You can see here low variances, and this is high variances. This is high bias. This is low bias. So if your model is high biased and low variances, the inner circle is the true values. So the prediction will always be here. It will be away from the true values, and that is called underfitting. If you keep high biases values while increasing the high variances, your data will have spread it around, but not on the true values, along the true values. Okay, so if your model has low bias and low variances results, you will have a right predictions. So the model should have a low variance and low bias, then you will have a correct predictions. And if you have high variances and low bias, your prediction will be spread out of your true predictions. It will just around here. And this is an example of overfitting, underfitting. If your accuracy on train is 0.24, 24%, and the accuracy on the training test data is 25%, this is called underfit model. If model 2 has training accuracy 95% and test accuracy 27%, then this model is overfit because it is predicting good on training data, but on the test data, on unseen data, it is not well generalized. So underfitting has low dimensional, heavily regularized, bad model assumptions, while in overfitting high dimensional or non-parametric, regularized, weakly generalized means. Not enough modeling assumptions, not enough data. So training model too complex can cause overfitting. If you train your model too much, it will become complex and will overfit. And if you make your model simple, it will result in underfitting. So you have to in between these two. So overfitting means on the training data, it goes to each data set. While in training, it passes to every data set. In underfitting, it just train on some of the data. While good balance is this. This is the good balance. Now here you can see the graph just to understand variances and biases. So at here, if you goes forward, the algorithm will become complex. And if you goes here, the error rate will be increased. So if you have low biased and high variances, low bias, if your model is low bias and high variances, so your error will be like this. And if you decrease the variances, if you decrease the variance and increase the bias, you are, as you increase in the biases, you are moving toward complex algorithms. And if you decrease the variances, you will move from complex to simple algorithms, but at the same time you are start increasing the error as well. If you start increasing biasness of the model get complexes, and at the same time it will increase the error as well. So you have to be in here in the middle to decrease the errors, and you have to follow the bull's-eye diagram: low bias and low variances. With this, you will have you are on safe side. So these are just a few points about adjusting or tuning your model. So we have gone through with the feature selections, and what are the techniques to get important features, their univariate feature importance and correlation matrix with heat map. We have seen some examples, and why we are doing feature selections. And after that, we have seen some correlation techniques, and which correlation techniques we're going to use. We just refer this table. If your features are continuous and response is continuous, then you can use for the Pearson correlation. If your features are categorical and response is also categorical, then you can use chi-square or wrapper methods. You just how many features you want to use in your performance. Should we use all the features or should we minimum? You have to work around, and how to work around, you just follow forward feature selection techniques or backward feature selection techniques, backward feature elimination techniques, or recursive feature eliminations. And after that, we have discussed biasness and variances. What is the biasness? We have seen that biasness is just underfitting, and variances is overfitting. Okay, guys. So for today, I'm done with this. And the next we have, I think, uh, some other topics like perceptron and Gaussian mixture model, and one more. An important one is multi-label classification. We will discuss this in next lecture. Okay, guys, take care. Bye. If you have any question, you just WhatsApp me or you can call me. Bye.